Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Okay, so the next talk is by Ran Gillag Bachrach, who is a researcher at Microsoft Research and was an applied researcher at Bing, and also a research scientist at Intel. He got his PhD at Hebrew U in Jerusalem in 2007 and has a lot of diverse interests in machine learning, healthcare, vision, combinatorics, and so on. And today, his talk is on deep learning, but not the kind that you were thinking of. And I'm very interested to find out what kind I was thinking of. He apparently knows what we're all thinking of collectively.
Yeah, I can read your mind. Thank you very much. I'm going to present the work that I've been doing with Chris Burges, and it's also based on earlier work that I was doing with Tali Tishby from the Hebrew University and Amir Navot, who's here, who just joined Amazon. And I'm going to talk about deep learning, but the notion of depth that I'm going to be using is not the one that we're using in the past couple of years in machine learning, but actually something that has been used in statistics for the past 40 years or so, but I'll get to that in a second. So let's start by talking about classification, just binary classification, just as a reminder. And so the common thing that we do when we encounter these kind of tasks, we pick a loss function, so the squared loss, hinge loss, whatever is your favorite one. We pick a regularization term to prevent overfitting. And then we come up with this energy function, which is just a sum of these things, and we minimize it. Right? So this is 95% of what we do in classification. And I would like to convince you that it's wrong. So to make it easy on us, I'm going to prefer looking at it as beliefs, as probabilities. So let's assume that this energy function that we're looking at is just the inverse log likelihood of some posterior belief that we have on the function that we want to select for making predictions. So minimizing this energy function is actually equivalent to finding the maximum a posteriori of this posterior belief Q. So essentially, we can think that the learning process that we do is we start with a prior, some prior, which is usually represented by the regularization term that we have. Then we see some evidence, so we construct a posterior belief, and then we select an hypothesis. And I'm going to focus only on the last step. How do we select an hypothesis given that we have some belief on the functions? So let's look at an example. So assume we have 9 functions in our class, and we want to select one function to be used for making inference. And to make it easier, we're going to have some icons to represent these functions. So you see we have donkeys on the left. They become a little bit more red as you go to the centers. You have elephants on the right. They become a little bit bluish as you move to the center. You have someone unaffiliated in the center. And you have the teapot on the far right. And now they have different sizes. The sizes just represent the amount of the belief that we have in each one of them. Okay? And now they have to make predictions on, this is our domain, x1 to x7, but again, we're going to use some icons. Let's call them bills. So they have to vote on the bills. And here is how they vote on the different bills. So, each one of them, they don't favor some of them. And obviously the teapot oppose everything. And on the right, I've marked the Q, the amount of belief that we have. So we believe some of them more than we believe the others. And now the goal is to select what are we going to use when it comes to make inference. So currently what we use is a maximum a posteriori. So we just pick the largest one, Actually, it's the one that shouts the loudest. So we're going to pick what currently we're doing in machine learning is just picking the teapot. And note something interesting about the teapot. It predicts on every bill that the label is -1. But if you look at the majority vote, the majority on every bill is +1 with larger margin. So it actually does not represent well our belief. So let's look at some other alternatives. So we can look at the Bayes rule, which is actually looking at the weighted majority vote on each of the bills. So this does represent well our belief, but when we go to larger audiences, holding the vote when it comes to runtime, to the real inference phase, is in many cases prohibited. So another alternative is the Gibbs law. And the Gibbs law said just whenever you want to make a prediction, just pick one of them at random and use it to make predictions. So this has several problems. One is that, again, making random selections at inference time might be hard to do. And second, that it's not deterministic, which is sometimes makes it hard to debug when you come to real-world problems. So we're going to propose a new approach, which is finding a deep hypothesis. And I'm going to define it precisely in a second. But basically, the idea is to pick just one hypothesis which agrees as much as possible with the majority vote. And we're going to measure the amount of agreement by this term depth. Again, we're going to define it shortly. But note that in this case, if you look at this small unaffiliated person, this small unaffiliated person actually agrees with the majority vote on every bill. So what we'll suggest over here is just let this person make the votes when it comes to the inference time. So again, the problem that we are interested at is the problem of hypothesis selection. And what are the desired properties of a good way to select an hypothesis given our beliefs? So we wanted to allow fast runtime in the sense that when we come to make a choice, when it comes to the point of making an inference, we want that to be fast. We want it to represent well our belief. We want it to be deterministic from the reason we just discussed. And we want it to have high breakdown point. So what do we mean by a high breakdown point? So let's illustrate that. Breakdown point is how much do we need to change our distribution in order to get an arbitrary output. So we have our belief, but how much do we need to change it in order to get a completely different outcome? So let's assume that we have, this is a representation of our belief. And if we're going to use the maximum A Posteriori, it's going to say that this is the hypothesis that we need to use. But now I can make a change of measure 0 and get a completely different outcome. This is usually not a desired property. So in this case, we'll say that the breakdown point of the maximum A Posteriori is actually 0 because we can make a change of measure 0 and get an arbitrary output. We would like to get our hypothesis selection method to have a higher breakdown point. So let's this table summarizes the properties of the different approaches that we discussed. So we get the maximum A Posteriori, which allows us fast runtime because we just have a single hypothesis that we're going to use to apply all the, when it comes to inference. But it has a low breakdown point and it doesn't represent well our beliefs. And we get the different properties of the different approaches. And obviously, as in any good talk, the method that I'm going to present is just absolutely awesome. So now, I hope I convinced you that the hypothesis selection problem deserves some attention and there is some problem with the current approach that we are using. Let's go in details into the approach that we are proposing. So we're going to present a method that just selects an hypothesis from the class that we have, which has the largest agreement with the majority vote, the weighted majority vote. And we're going to show that actually this choice allows us to get good generalization, fast runtime, and all these properties. And in order to motivate it, let's go back to look at the one-dimensional median problem. How do you find the median out of these blue points that you have on the line? But we're going to do it using a notion of depth. So let me define the steps as a process. So what you do when you get this point, you just split using a threshold these points into two groups. You count the number of points you have on each side of the split. So for each point, we just mark the number of points with which it agrees. So it agrees with the point which are on the same side of the split with it. And then we minimize over all the possible splits. So I don't know, how, it might be hard to see, but the point on the far right has a depth of 1, and then we have 2, 3, 4, 5. And the point in the middle has a depth 6. This is the deepest point. And the deepest point is also called the median. So this is how we do it in one dimension. When we go to the multivariate case, Tukey extended this definition in the following way. Again, we split the space in two, but this time instead of using a threshold, we're going to use a hyperplane to split the space. Now we count the number of points we have on each side of the split. We minimize over all the splits, and the deepest point is the median. Now the nice property of deep points is that whatever split we're going to choose, the side in which this deep point falls in has many points. Right? So it's, in a sense, it's with a large agreement with at least a significant amount of points. Just a word of warning, unlike the one-dimensional case in which there is just one proper definition of a median, in the multivariate case, there are multiple different definitions, and the one that I just presented is just one of them. But we're going to take it and extend it to the class that we're interested in, which are classification functions. So assume we have a set of functions, capital F, and each function in this class is just a binary classifier. Every point, x, splits this set into two parts. The function that labels it y plus 1 and the function that labels it minus 1. So again, this is the same kind of split that we saw before. And now we want to count the number of functions that we have on each side, but since it might be a continuous set of functions, instead of counting them, we're going to look at the measure of the functions that we have on each side of the split and assign for each function this conditional depth, which is actually the measure of the side of the split it belongs to. And finally, we define the depth of a function to be just the infimum over all possible splits, which is actually infimum over all points in our domain. And this is going to be the depth of the function f. And again, once you have a definition of depth, you have a definition of median, which is just the point that maximizes the depth. The Tukey depth that we saw before is just a special case of this depth that we just defined when we're using some variant of linear classifiers, which is called linear threshold classifiers. I'm not going to go dive into that, but the reason I'm bringing it up is that for this class of function, we know that actually for any belief Q that we have, actually there are deep functions. So if our domain is linear threshold classifiers in dimension D, there is always a function of depth at least 1 over D plus 1. But if Q is actually a result of using an energy function, which is convex, then there is always a function of depth 1 over E, when E is just a natural number. And this is independent of the dimension. The reason I bring it up is to show that actually this definition we came up with is not void in the sense that indeed deep functions exist. So now let's ask ourselves, what are the theoretical properties of these functions? So here's the first result. This result shows that the generalization error, which is what we denote here by the risk of the function f, is bounded by 1 over its depth times the expected generalization error of the Gibbs classifier. Right? Note that this bound is true always. It's not with high probability. It's not no constraint attached. It's always true with every dimension, and actually it's easy to prove. And for example, if we look at the weighted majority function, so the weighted majority function always has a depth of at least 1/2. And if you plug it in this bound, you'll see that the generalization error of the majority vote is bounded by twice the generalization error of the expected generalization error of the Gibbs classifier. And this is a well-known result. So this is just one way to apply this bound. But actually, this bound is true for every function. We can plug it into Bayesian bounds and get kind of a more standard generalization bounds. And I'm not going to dive into all the notation over here, but the things to keep in mind is this bound shows that the generalization error, which is what we see over here, you can see it, but the generalization error is bounded by some 1 over the depth times this bulky term b, which is actually a function of just training error. So we can get a bound for a generalization bound for every function in terms of its depth and some training error term. Now, the depth that we introduced seems to be a little bit too restrictive because we define the depth in terms of the infimum over all possible splits. What if we have something that is with larger agreement with large portions of the function classes on most points, but not on all points? So we can define a relaxed version of this depth function, which is the term that you see up there. And again, I'm not going to go into the exact notation, but what to keep in mind is that it basically says it's the same notion of depth that we had before, so we look at minimizing over all splits, but a fraction of size delta of the splits. So this is a relaxed depth that we see on top, and at the bottom we look at the version of this depth function when we just have a sample. So we take a sample of points, and this sample actually is a set of splits, and we define the depths to be just minimizing over this set of splits instead of going over all the splits. So these are just kind of relaxed definition of depth. And for these definitions, we can prove the following. The first thing is we show that we can bound the generalization error of a function in terms of its relaxed depth. So again, we get a bound of the form of the generalization error of a function is bounded by 1 over its relaxed depth times the generalization error of the Gibbs classifier plus some error term delta. And we also have this relation between the different definition of depth, which is the depth is always smaller than the empirical depth, the one that we compute only over a sample. And this one is with high probability smaller than the relaxed depth. So they are all of them are pretty much tied together. We mentioned before the problem of the breakdown point of the maximum a posteriori. And if you remember, we talked about the fact that you can make a change of measure 0 to your belief and get an arbitrary output from the maximum a posteriori. This is not true when you're choosing the median as your hypothesis. And again, we can bound the breakdown point of the median in terms of its depth. So the breakdown point of the median is something like its depth divided by 2 minus some term p. But again, it showed that if you indeed manage to find a deep hypothesis, it's going to be robust. So I hope that by now I convinced you that the median and the depths are interesting things to look at. But the next question that we're going to ask is, can we compute them? Can we find them? And I would like to convince you that this is possible. And we're going to show an algorithm, a very simple algorithm that is capable of doing it. And let me illustrate this algorithm. So assume we have our belief Q, and now we want to find or approximate the median. We take an unlabeled sample of points, and we compute for each one of them the probability of each one of the votes. So what is the fraction of our, kind of the weighted fraction of our distribution that votes that the label is +1, and what is the fraction that says that the label is -1? So here, for example, on the first instance, we see that 80% of our classifiers say that the label is -1, and 20% say that the true label should be +1. So these are the desired labels that we want our hypothesis to assign to these points. And now we can try to find a function which is consistent with all these labels. If we can, if we're lucky, that's good, but assume we're not. If we're not, we're going to eliminate one point from the sample. And we're going to eliminate the point for which the majority is smallest. So if you look at this point marked here, point number 6, indeed the majority said that the label is -1, but the majority is only of size 55%. That means that even if we have a classifier which disagrees with this point, it still agrees with a large portion, at least it agrees with 45% of our voters, which is not too bad. So we're going to eliminate this point from our sample and try to find a classifier that is consistent with this reduced set. And we're going to keep on going and eliminating point one by one according to the size of the majority vote until we find something that is consistent with the subset. Again, we can accelerate this process a little bit by using binary search, but for the sake of this presentation, let's assume that this is a linear search. And now we're going to claim that the hypothesis that we've found, which is consistent with the subsample, is indeed going to be a deep hypothesis. And not only that, we're going to claim that its empirical depth is actually the size of the minority vote on the last point that we eliminated. So that's the thing that I want you to remember about this algorithm, that the only thing that it requires is a consistency oracle. A consistency oracle is an oracle that, given a sample, either finds an hypothesis which is consistent with this sample, or say that such one does not exist. This is much simpler than trying to find an oracle that minimizes the error, for example. So this oracle only says, here's a function that has 0 error on this sample, or say that such a function does not exist. So here's a more formal definition of this algorithm. I'm not going to go into it, but much like the previous talk, I'm just going to show you that it's short. So this is the entire algorithm. And now for what we can say about this algorithm. So first of all, it's good in the sense that it will always stop and always return both a function and a depth for this function. The depth that it's going to return is indeed going to be the empirical depth of this function. And more interesting is this result, which show that with high probability, and I'm not going to go into the exact terms that we have here, we have this property which says the following. the relaxed depths of the function that this algorithm is going to return is with high probability greater than the depths of the true median minus epsilon. So if there exists a deep function, this algorithm will find a good approximation for this function. So I'm getting close to finishing this talk, and here are the things that I want you to remember. So first of all, the common thing that we do in classification and other tasks is using the maximum a posteriori. Let's question that. I'm not sure that that's the best approach that we can use, and I hope that I was able at least to get you to question this assumption. There are other approaches that we can use, and we presented one over here, which is using the predicate depth and predicate median, and we show that they have some interesting properties. And in order to compute them, we need only a consistency oracle. The reason why I bring it up is because since we are so used to use the maximum a posteriori, which requires minimizing the energy function, we actually force all our energy function to become such that we can actually minimize them. So, if someone is just looking at recent machine learning publications, one might assume that the word is convex. No, not everything is convex, but we were forcing it to be convex because we were looking at the maximum a posteriori all the time. There are other things that we can do that do not require convexity. The main result that we've shown were defining the predicate depth and median. We showed generalization bounds, breakdown points, algorithm for both approximating the median and for estimating the depths of the function. I didn't have the time to discuss that. We also have analysis of the geometry of the depth function and some interesting relation between the depth function that we came up with and the Tukey depth. There are several open problems here. The algorithms we presented require the ability to compute probabilities or to sample from our belief function Q. And therefore, we need to first come up with good belief functions, which are not restricted to be convex, but ones that we can either sample from or compute probabilities using these functions. We also think that using the algorithm that we presented here, we can improve upon algorithm for computing the Tukey depths, but this is yet something that needs to be proven. And finally, although I was advocating for using the median, don't use it while driving. Thank you very much. Yeah, thank you for the question. So the question was we were saying that you have the belief, and you cannot just use the entire belief when you make inference. And we suggested using a single function to kind of summarize the belief, but maybe it's a better approach to actually summarize it using multiple functions, or you call it quantiles. That's a very interesting idea. We were thinking about it, especially if you kind of, again, regain our intuition from the one-dimensional space, whereas if you have a multimodal distribution, you actually, if you want to summarize it, you don't want to remember just one point. Actually, you want to remember the modes. So I'm very much interested in that. I was not capable of finding a good way to do that. So. Yeah. So the question was, in the talk, we kind of assumed that we want to find a function, the median, from the same set of functions on which we developed our belief. But why do we have to restrict ourselves in that way? And that's absolutely right. We only did it for the sake of presentation because maintaining two sets of functions would be too cumbersome. But indeed, if you have your belief defined on one set of functions, you can measure the depths and define the depths and the median with respect to any function. It does not have to be in your space. So for example, the Bayes rule, the weighted majority, does not have to be a member of your space, but still I can prove that its depth is at least 1.5. So that's absolutely right. So first of all, what you said, that actually what we're doing here is indeed deep learning, and coming from you, I take it as a compliment. So it's kind of the more commonly used notion of machine learning, of deep learning in machine learning. So I take it as a compliment. And the question was, when you have a large amount of data, actually the prior does not, actually is irrelevant, right? So you can almost ignore the prior and just use the data. The method that we present here is actually independent of the way you come up with your posterior belief, right? So I just described this process of starting with a prior and then coming up with a posterior, just as, tying back to what people are more commonly used to. But actually, if your posterior belief is generated by using some unlabeled data, some semi-supervised data, or maybe actually you were doing active learning and actually maybe it's not a random process, I don't care about it. At the end of the day, you have a belief. And now, how do you convert this belief into a function that you're going to use when it comes to inference? Right? So it's, the way I see it, it's completely independent of the process that you were doing in order to obtain it. So indeed, when you have large amount of data, actually prior is not that important. I'm okay with that.
So basically, in your the development of theory, you don't make any assumptions about the site.
Yeah.
Maybe one more very, very, very short question.
I really like the idea.
So the question was, about sampling from the posterior queue, which could be hard. And can we cheat, quoting your, can we cheat using bootstrapping or other techniques? You know, I'm all for cheating, so. Yeah, so this is why I presented it as an open problem, right? We need to come up with good ways to do it, and cheating is fine, right?
So the next speaker is Matthias Dutren from the University of Washington Department of Statistics, where he is a full professor. He was also a full professor at the University of Chicago in statistics, and is a winner of the Sloan Research Fellowship, the NSF Career Award, and a number of other things, and has many interests involving graphical models, algebraic structures, and model selection. The talk is entitled A Bayesian Information Criterion for Singular Models, and he told me beforehand that he was going to add, it's not the Bayesian that you were thinking of.
Okay. All right, so this is joint work with Martyn Plummer, and some of the things I show that based on some computations done by two students, Vishesh and Dennis. So I'm going to revisit a very classical topic, the Bayesian Information Criterion, which I think many of you know. Some of you maybe like, some of you don't like, but okay, this will be conditioned on your opinion, and we'll talk about this and revisit this. And so the types of questions I want to look at is for a data set like the one depicted there. This is about velocities of galaxies, and it's one of these obnoxious data sets where there's about one paper or maybe two papers per data point written about this. And so in a problem like this, you might be interested in fitting mixture models and finding out about group structure and determine how many components should you include for a mixture model. Okay, and so problems like this will be the topic of this talk. And okay, and so there's, as we've already seen today and heard about today, there's many different ways you can go about model selection problems. And there's some, when you have a predictive problem, you might just focus on what you really care about and cross-validate or use some computationally cheaper routes to address what you're actually interested in, right? That's the desirable thing to do. But in some cases, maybe unearthing group structure, unsupervised situations, maybe it's not so clear. So I think there's also a place for Bayesian and Bayesian-inspired approaches to model selection, and that can take the form of a little bit of what was in the previous talk, of sort of fully Bayesian model determination, where we're very serious about priors and try to compute posterior quantities as well as we can. And then this relates to different approximation schemes that you may be familiar with under the name of Laplace approximation. And in a very crude form, following that same idea, Schwarz's Bayesian Information Criterion. That's based on this paper that he published in 1978, Gideon Schwarz, and I think that's one of the most influential papers in the field of statistics. And so I'm going to take a few minutes and just review that, what the idea was for this proposal for a score that you would attach to models and optimize to pick one if you have to, or to get some assessment of uncertainty over for model choice. So I'm just going to consider the most basic of setups possible. So we're going to look at a situation where for some sample size n, I'm going to get to see a bunch of observations that are all drawn from the same distribution that I'm going to call pi up here, and they're all independent of each other. And so I'm going to use yn just to denote this object of n observations that I get out of this observation process. And then I'm in a situation where I want to contemplate different models for this observation process, and so modeling means writing down a bunch of candidates for what this distribution pi might be, and so associated with a particular model, you have then a likelihood function that maps the distributions in your model to, in the discrete, or in the case of discrete data, simply the probability of seeing the data that you got on the distribution from that model. And pragmatically speaking, the BIC, the Bayesian Information Criterion, is this model score that you get by, for a given model, optimizing this likelihood function, and then taking a logarithm, so down here. Okay, so pi hat is a maximum likelihood estimate. And so you take this quantity that you can make larger and larger as you pick larger and larger models, and you subtract from it a model complexity term that here takes this form. So there's the dimension of this model, so I'm assuming that this is meaningfully defined. There might be some parameter counting you're doing in the simplest situations. And you divide that by 2, and then you bring in the logarithm of the sample size. And this is the score that's widely used and computed by many software packages and so forth. And so this has one feature that this has is a property of consistency. So if there are actually true models you're considering, then you would find a most parsimonious true model for large enough sample size n. And just to review where this comes from, this score. So there's obviously this very particular combination of how the sample size is brought in and how model complexity is brought in as it's measured by a dimension term. And so to review this, 2 slides. So this, as the name suggests, Bayesian Information Criterion derives from Bayesian ideas. So in a Bayesian approach to model selection, we would be specifying prior probabilities on, let's think about a finite set of models, like a certain possible number of values for the number of mixture components, and maybe I'm operating with an upper bound on that. So I have some finite collection of prior probabilities in what I'm going to consider here today. Those we have specified, and maybe we'll just go forward and think of all of those being equal for now, and so there's nothing informative going on, although it's not going to really matter for anything I'm going to say later, whether you have something in mind here or not. And then what you want to calculate is the posterior model probabilities, so the probability associated to a particular model given an observation, or a set of n observations, really, yn. And in order to calculate this, so you see that you have to calculate, or that these probabilities are proportional to this product of prior model probabilities, and this term here, which is an integrated or marginal likelihood. So what you do there in this term here is you're integrating your likelihood function with respect to the prior specified in a given model. Okay, so if you think it's pi as just some parameter to some distribution, then you have a prior specified for a mean parameter, say, and this likelihood function is a function of that mean parameter, and you're integrating it. Okay, and so if you're Bayesian and you can compute this, end of story, you get a bunch of numbers out, and that's it, right? But as was just mentioned in the questions, this can be tricky, right, to compute this. And if you want to have a piece of software that runs fast, maybe you're interested in various hacks to get something crude and fast. And so this, so one way of getting at that is to bring in asymptotics, to think about large sample sizes and think about what happens to quantities such as these posterior model probabilities, or equivalently this marginal likelihood, when you again think about a paradigm where data is drawn, is random, is drawn from some distribution, okay? And so let's think about this. So I'm going to think about my observations again as random. They're drawn from some distribution. I'm going to denote pi 0 here. And let's make explicit, we're thinking about some case where we have a parametric model. So our distributions in our model script M are associated with choices of parameter vectors omega that live in some Euclidean space R to the D. Okay? And so Now I think about yn as random, and therefore when I think about the marginal likelihood, this is just a random variable, right? So for every sample size, I have now a random variable. And if I so wish, I could consider its logarithm. So I have some random sequence of random variables now. And then the thought of Schwartz was, let's study what happens to this random variable for large n, and see what guidance this provide us with. And so and then what happens here is, I'm just going to say, for nice priors in nice models, you're going to have this result holding. This sequence of log marginal likelihoods, these random variables, are equal to the logarithm of the maximized value of the likelihood function minus dimension over 2 log n. So those are all the terms that change in a very important way with the sample size n, plus a remainder that's bounded in probability. Okay, so just something bounded. And there's been various follow-up work showing that you can also estimate this remainder term and get an honest approximation out. But I'm just going to stay with this crude observation for now, that the pieces that change in a very important way are these two, and just picking out those two, that's the Schwartz's proposal for a score to attach to a model. Okay? All right. The important thing to notice here that somehow magically we've gotten rid of the unknown distribution pi0 that I generate data from here. So this model complexity term here is not affected by whatever distribution you start with here, as long as I'm in some sort of nice model situation, okay? And what I mean by this nice model situation, also to drive this point home visually, so in a nice model, this marginal likelihood, that's an integrated likelihood function. Think about the integral of a likelihood function as the integral of the exponential of a log likelihood function. Think about doing a quadratic approximation to a log likelihood function as you do in any graduate course in statistics. And then maybe I can convince you that really what's driving this result here is the behavior of integrals like this. It's the integral of e to the minus the sample size times some quadratic in the parameters, okay? And if you then think about how does this integral behave as n changes, you know, I'm making some pictures of its graph there. What I'm asking you, what's the area, the volume under this surface here? And you see that decay. And what's being figured out on this previous theorem is the rate of decay, right? And that rate of decay determines our model complexity that we're using to define a model selection score. And so for this, obviously, it's totally trivial for you to work out that an integral like this here in 2 dimensions decays at rate 1 over n, okay? And this is just one instance of this phenomenon of putting things on a log scale. You're seeing this decay rate leading to 2 over 2. I'm writing a 1 in an artificial way as a 2 over 2 log n. And here you see the 2 that is the dimension that I'm talking about, okay, in the 2-dimensional case. Okay, and so in nice models, it's really only integrals of this type we ever have to think about, and it's really only decay rates of this type that we get out, and this is how we get our model scores. Now, this is not all in terms of what you can encounter in statistical practice. So the key idea is this quadratic approximation, and this is sometimes not possible in scenarios where identifiability, for example, breaks down, because maybe your true distribution is one that you can represent with as a mixture of 2 components, but the model you're considering is mixtures of 3 components, okay? And you have non-identifiability issues, and that will lead to your not being able to approximate the log likelihood function by a quadratic form, positive definite quadratic form, okay? And there's lots of applications, so there's lots of scenarios where this can happen, and those are the ones that I'm going to call singular, okay? Singular problems. And anything you can do with a latent variable will have that feature, really, okay? And just to give you one silly example here, If you can't do a quadratic approximation, what sort of other things can you encounter? Well, you could encounter something like this, where instead of a sum of two quadratics, I have a product of two quadratics. And that captures what the log likelihood function behaves like in the vicinity of some given point. All right? If you're looking at a function like this and you ask how does the area or the volume underneath this surface change with the sample size n, and you're going to find something different, right? And so you can go and work this out over lunch, or just believe me for now that just if you look at it, I mean, should it be slower or faster decaying? Well, if you just look at this slice here, it sort of decays like a one-dimensional thing, right? And if you look in the middle, there's somehow a little bit more volume bunched up there. And so it turns out that this quantifies to a rate log n over square root of n. Okay? So something else is happening. And in some ways, this example is general. So there's a guy in Japan, Sumio Watanabe, who's been working on this and has produced a whole bunch of work in the last decade that culminated in theorems of this type. So if we go away from scenarios where I have nice identifiability of parameters and so on, but keeping with some nice structure, and I'm not going to say exactly what, but there's a good amount of technical assumptions that go in it, but it'll be applicable to an example like selecting number of factors in fact analysis, or rank in reduced rank regression, or number of mixture components in certain mixture models. You're going to have a theorem that says that you can still get study this behavior of the log marginal likelihood. You still find that this is the same as the logarithm of the maximized value of the likelihood function. You still get, there's some decay that on the log scale gives us a log n term, log sample size. Now, as we've seen in this previous example, there was a log n term on the original scale. So on the log scale, there will be a log n term. If you care about that, maybe we don't really. And then there's going to be constants out front, where this is under analyticity assumptions, a rational number, lambda, and this is an integer m here. And this is going to be, in general now, a function of what the true distribution is. So in particular, to visit this example of mixture models, if I look at a mixture model and I want to, and say let's fix, it has 3 components that it allows that you get to mix. If I'm studying the log marginal likelihood coming out of some Bayesian setup, when I generate data that is drawn from a distribution that you can specify with only 2 components, right? You'll find something here. And if you can specify the distribution with only 1 component, you'll find yet something else here, okay? And so in these types of problems where you have this singularity where doing quadratic approximations isn't everything that you need to do, you're going to face this problem that this theorem here, it's nice, it applies, it gives us information about this sequence that we're interested in, but its behavior now depends on what is the distribution that I generate my data from, okay? And so this is nice math, but it's completely useless for statistics, because if you knew that, you wouldn't be asking these questions in the first place. All right? And so this is this bottom point there. So this term that you might want to use as a model complexity term depends on how you generate data. But if you knew how you generated the data, then you wouldn't be asking various statistical questions, right? Okay, so what our paper is about, and this paper that has that same title as this talk, is about trying to leverage this mathematical information to get a different type of score out for model selection. Okay, and so we're in a situation where if we knew the true data generating distribution, I would have an approximation. And I don't know that, so what can I do? So ideally, if you're Bayesian, sort of the uncertainty about a distribution like this really should be based on posterior quantities, right? But the posterior quantities are the ones that you can't calculate, otherwise you wouldn't be doing this in the first place, right? So, but we're trying to aim for trying to bring in relate to posterior information or information quantified by the posterior distribution. Okay, but before I go there, let me say a few more things about problems that one sees typically in practice. So again, the setup I'm considering is I have a finite set of competing models. Just think of I telling me the number of components that I should use for a mixture model, okay? I usually have some nice ordering going on. You know, if I can express a distribution with 2 components, I can express it with 3, right? Trivially, and so on. As I said before, if I knew the data generating distribution, I would have an approximation to a marginal likelihood of this type, putting this theorem back on the original scale by exponentiating that display that I had on the previous slide. And then our approach is to take and average all these approximations, okay, where you average out over choices for pi 0, okay? And ideally, we'd want to do this averaging with respect to a distribution that is somehow close to a posterior, okay? So this seems a very daunting task, but it's not quite as complicated as I make it look right now. So there are certain things that are typically the case in these problems that I want to deal with, like mixture modeling. There's a smallest model that is regular, for which all these issues of where quadratic approximations are always okay, and what Schwarz proposed is perfectly fine. And if you think about mixture models, there's a start where you might want to start with just one component, right? This is always identifiable then if you say talk about a normal, and it's just I don't know, the model of normal distributions with unknown mean or unknown mean and unknown variance and so forth. In reduced rank regression, there's a case where you maybe have covariates actually don't tell you anything about the outcomes, rank 0. When you start looking at dependence models where you throw around latent factors, you might want to start with thinking about there being no independence at all. And so there's some starting point in which you have a regular model. Then it's also true that this dependence of these coefficients, lambda and m, the way they depend on the unknown data generating distribution is not in some continuous complicated fashion. They're sort of step functions. And so the way this usually works is just like it is in mixture models. It'll be the case that if you're a generic distribution that you get by mixing j components, and you think about the marginal likelihood of the model in which you have I components and I is greater than j, then there'll be some fixed value for the lambda and the m, okay? And so really I can think about there's an approximation for every pair of models, a submodel embedded within a larger model. And so in mixture models, distributions represented with fewer components and so forth, fewer factors, lower rank, and so on. And so here's how our method works. I would like to, if I'm in this scenario here, this averaging is really actually just a weighted sum, because I'm computing the integral of a step function, the way I presented this overly complicated. I'm really only doing a weighted sum of approximations, and these are the approximations that I get from the theory when I knew that the true data generating distribution was representable with j components, and I talk about the model with I components. The weights that I would like to use are posterior model probabilities, right? Wouldn't that be nice? Okay? But obviously I don't know these. The posterior equivalently put, I can write this in terms of the marginal likelihood of these models that I'm considering, and I don't know. And what we then do is, here, what I want to compute is an average over here. The quantities that I want to compute appear in the weights. So I'm just going to equate those two and think about the approximation on the right-hand side as well. And it turns out what I wrote down is a recursive system that you can solve nicely and that has a unique positive solution that gives me what I want. Okay? And so maybe what you should just remember here, it's a way of forming a weighted sum of different approximations. Okay? But it turns out to work out in a very well-defined way. Okay? And so now we can think about how this relates back to Schwarz's proposal. So if you're in a situation where none of these issues arise, our proposal reduces back to what he did. There's properties of consistency, recovering most parsimonious tree models, and you're more honestly Bayesian in the sense that this criterion that we propose and call the singular BIC is equal to the log marginal likelihood up to a remainder term that is bounded. Okay, and that is would not be true for the Schwarz's score that's based on dimension. And here are just some little examples. So what I'm showing you here is just how good is this at selecting the right rank. So I'm just simulating, and for sample size increasing, you see blue bars and red bars that are frequencies of, I generate a data set, I use my criterion to infer a rank. What rank did I infer? And then these are histograms. And so you see that initially, so this blue score, that's Schwarz's score, is penalizing based on a much too heavy penalization, and it's under-selecting the rank. True rank is 3, and our proposal is that red thing that is much quicker at picking out the correct rank. And it's much more honestly Bayesian. So here's some computations for factor analysis, where on the left-hand side there's honest, Monte Carlo honest posterior probabilities for the number of factors, and here's sort of approximations based on Schwarz's BIC and based on ours. And you can see how Schwarz's BIC very quickly becomes very overconfident on some small number of factors. Dimension is true, stronger penalty, and ours is a bit of alleviates that. And as a last one, I'm going to go back to this mixture model example here. And so let me just maybe put up this picture, which is again another picture of estimates of posterior model probabilities. And what you would see here is Schwarz's criterion would say with absolute certainty, we're going to be in a situation where 4 components are appropriate. Our proposal says, well, overwhelmingly 4, but there's some doubt that maybe remains about maybe you needing a few more extra components. And now this is obviously totally subjective, and I could put up really anything I want, but this is one that the black bars are posterior probabilities that come out of some paper describing these obnoxious galaxy data, okay? And so the point here is that, okay, there's a big disagreement from me to these black bars, but there's the phenomenon that's always observed is that something like BIC is just putting far too much weight on a small number of components compared to what Bayesian methods actually do. And our proposal gives a little bit of, alleviates this a little bit, okay, in this example. And that's it. So here's the reference down there. But so as a gist of it, so this Schwarz's proposal, Laplace approximations, they're not appropriate fully for problems like determining components or number of components in mixture models. And what we propose is something that I would say maybe deserves the name Bayesian Information Criterion for these problems. Okay, thank you. Yeah, so Carlos asking about how long it would take to compute our criterion compared to the standard proposal. And so that's a great point. So the way I defined this is I said, so you should solve an equation system like that. And what this really says is when you think about a model in which you mix, say, 7 components, you should really think about how well do models with fewer components fit, because a large sample theory-derived approximation to a marginal likelihood will depend on what I think about the number of components, right? And so in my proposal, the way this goes, for something like mixture models, it really isn't the problem, right? I'm assuming that you're able to fit all the models with 1, 2, 3, 4, 5, 6, up to your number of components you want to consider mixture models, and then this will be essentially as fast as computing Schwarz's criterion, because it's just, you have to fit all the models, and the post-processing step after that is really trivial. But if you were to look at some problem that is big, has a big model space, like, I don't know, you have to select tree models, trees on a big number of nodes, then this is going to be infeasible, right? And Schwarz's criterion is that you only have to look at one model at a time, which is great for something like greedy search and so on, whereas we'd have to think about what to do for those scenarios. Yeah, so I haven't done a good comparison to those yet, but yeah. But in principle, anything that's based on quadratic approximations, Laplace approximations should be breakable in these cases. Yeah, so this was a question about if you had special structure, for example, shared parameters across the distributions in different components. So, so the values for these constants that make up these approximations, Li, Ij prime here, those will depend exactly on this. So, you know, the value of these constants here, they will depend on the fine structure of what you do with your mixture distribution. For example, in a Gaussian case, the easiest thing would be to make a variance common to all components or not common, and that'll be giving us different numbers up here. And yeah, and so that's difficult. I mean, so to be honest, you know, if I give you a complicated enough model, you computing the dimension is a very, very difficult mathematical problem. And computing these values of lambda and n, let me say something like exponentially harder, okay? So this will be possible for some cases and for some not. And if you can't, then you can maybe operate with bounds, or you can operate, or you have to do something entirely different.